Hi everybody, I'm Ian Cunningham. Welcome to this episode of Engineering a Jigsaw, a 50,000 piece jigsaw puzzle. Let's see what we're going to cover today. Well, in this episode, we're going to look at some of the things that have become part of the EE system of a modern vehicle over time. So we're going to start back in the past a little way, and then we're going to have a look at the modern day and maybe even a little glimpse into the future. There are no prerequisites for this episode. So once upon a time, or at least up to the 1970s or thereabouts, most vehicles that you'd find on the road and that you and I would be riding around in, if we were alive at that point in time, would have had very, very few electronic components. So often all you would find would be electrical parts to start the car, to have lights, so headlights, indicators, and ignition systems in the case of a petrol engine, and nothing else. Some cars didn't even come with a radio. Gradually, though, vehicle manufacturers started to introduce other small electrical systems. So, for example, remote central locking, meaning you no longer had to fumble around with your keys to try and find a keyhole in the dark, maybe in the rain, to get into your car. You could press a little button and you would be able to get into your car nice and easy. And these small electrical systems made use of electronic control units, or ECUs for short. ECU is a key term. We'll come back to that time and time again. And ECUs were used to apply rules and also, or alternatively, to perform calculations. So we have these little tiny control units in there, able to do a little bit of maths and to apply a little tiny bit of logic. So maybe to control when things are able to be turned on and off rather than just letting them be turned on and off whenever. And of course, this means that the ECUs were wired to sensors and motors and other actuators, so lights, horns and things, actuators, to provide these functions. Now, each sensor, actuator, connector or wire that goes into a vehicle means more cost and weight is added to the vehicle. Cost and weight are bad. Okay, so weight, because the more a car weighs, the harder it is to accelerate. The harder it is to accelerate, the more fuel we need to accelerate it. And that's a running cost as well, so it's kind of double cost. Obviously, if we have to make more expensive parts into a car when we're building that car, so we have more wires, for example, which costs more, then people have to pay more for the car. If it costs more to build, it costs more to buy. So cost and weight, generally things people want to try to reduce as much as possible in designing a vehicle. People, though, soon got to thinking, well, what about if the ECUs themselves could be wired together? So if we've got a braking ECU, which is able to detect if the wheels are spinning as well as locked and skidding, well, that would be able to send a signal to the engine ECU to say, just reduce power for a little while because the wheels are spinning. And of course, if the power is reduced, the chances are the wheels will stop spinning. And this is what we call traction control. So we have this ability of the ECUs to share some information and put new features and functions into the vehicle, but they need to be able to share that data. Now, we don't want to necessarily put a wire in for every single piece of information that needs to be shared. So people realized rapidly that ECUs could possibly use networks to send and receive data between themselves. And networks are actually the foundation of where Vector started. So Vector started with tools, software tools that engineers could run on PCs to understand what was happening on the networks in vehicles that they were working on. And the ability of ECUs to communicate and having just this little bit of intelligence also led to some other interesting possibilities. So what else became possible? Well, in the late 1980s, mid-80s, regulations were introduced to control pollution through exhaust emissions. And these regulations also said that ECUs must be able to detect and report, upon request, questions that might be able to cause excessive emissions. This is called onboard diagnostics, or OBD for short. You may have heard of OBD before. Diagnostics, of course, is another job for ECUs to do. And diagnostics is more than just OBD nowadays. We have diagnostics for everything that's electrical in the vehicle. So our central locking system will have diagnostics in it. So to detect maybe if one of the door locks has stopped working correctly. Our braking system will have diagnostics in it to check that the ECU is able to detect that the wheels are turning or not, and so on and so on. So diagnostics, really important. It's what you and I rely on anytime we take a vehicle to a workshop when we think there's a problem. The workshop will put a diagnostic tool to the vehicle to understand what's happening and then be able to fix the problems in there. Now, to reduce costs, vehicle manufacturers also started to look for ways they could use a single ECU in different but similar vehicles. So this reduces the cost needed to develop the vehicle, and sometimes they're able to get a cheaper price by having a higher volume on the parts they were buying. And this meant that they developed a concept of calibration or tuning. So you take an ECU and then you make some small adjustments, you perform some tuning to make that ECU work in different vehicles. So in the case of a braking system, maybe the vehicle is got a slightly different weight, maybe the weight is split slightly differently between the front and the rear axles on different vehicles, but you want to use the same braking system in the vehicles to reduce your overall costs. So you have this idea where we can tune the braking system to accommodate those differences in the system. So calibration tools and calibration capability were then built into ECUs to allow this. And of course, computer science didn't stand still. And as computer science has advanced, people have gradually increased the thinking power of ECUs. So from being single core, relatively simple processors, maybe even just an 8-bit processor in the early days, we now have multi-core 32-bit processors are quite common in vehicles. And nowadays, of course, we're starting to see things that are much more like the kind of processor even you'd see in a PC or a smartphone starting to come into vehicles. So the really simple stuff that we started with is becoming much more complex. And this is because people have wanted to start to put things like artificial intelligence into vehicles to allow them to process video streams, radar or LiDAR data to be able to understand what's going around them and then take actions. As well as this, some vehicles even use off-board computation to limit the amount of processing power that they need in their ECUs on board. So in this case, we maybe have an ECU which is able to pick up data from GPS satellites to know where the vehicle is. The vehicle is able to communicate over the internet to a server. It's not the only one doing this. There are many, many, many vehicles communicating with that server perhaps. And then the server is able to perform calculations, maybe tell the vehicle automatically how to get around a traffic jam that a number of vehicles have become stuck in, and so on. So this, of course, means that vehicles don't just contain networks. They're starting to become part of networks as well. So the complexity is rising. Now, if we go back inside the vehicle just for 1 second and think about the complexity of a modern vehicle EE system, what do we tend to find in there? Well, over 100 different ECUs. So the examples we've given so far are quite simple. I've talked about just 1 or 2 ECUs, 5,000 wires and connectors, maybe 15,000 signals on those networks. And once we put in sensors, actuators, fuses, and other electrical components, it's really easy to end up with over 50,000 pieces. Really, really easy. And to develop all this means you've got to manage all these thousands of pieces and make sure they fit together correctly and also can be maintained. It's no good if they break and you can't work out what's broken. We need to be able to make sure we can fix our vehicles when things go wrong. So that's the end of the content we're going to cover in this episode. So as a summary, we've given a high-level overview of how vehicle EE systems used to be really simple, no ECUs at all, in fact, to begin with. Then, as ECUs came into the vehicle and we wanted to be able to share information between them but minimize cost and weight, we introduced networks. The introduction of networks allowed us to bring in more capabilities, such as diagnostics and calibration. And over time, the EE system of vehicles has become much more complex. And even vehicles themselves, as well as containing vehicles, are starting to become part of networks in their own right. So, what can we look at next? What's coming up? Well, we've got other Engineering the Jigsaw episodes planned. In particular, we have an episode, What is an ECU? And as we see in that episode, an ECU is another 50,000 piece jigsaw puzzle. We're going to have an episode on networks in vehicles. We're going to have an episode, What is diagnostics? An episode, What is calibration? These will all be coming up in the series in the future. If there's additional topics you'd like us to cover, please let us know using our email address. I'll give you that in just a moment. If you can't wait, then our e-learning and our webinars via the website and our YouTube channel, you can find much more about networking technologies and the other technologies going into modern vehicles. You can also, if you want to, get detailed technical training from the Vector Academy on the topics that we've talked about today. So that's all we've got time for. Thank you for joining us. My name's Ian Cunningham. Please do email us at engineering.jigsaw@vector.com if you have any questions or if you have any ideas for topics you'd like us to cover in the future together with you. We'll see you soon for another episode. Bye.